In this video, we are going to talk about the sampling distribution of the sample proportion. Okay, so let's first talk about what exactly a sample proportion is. So what we've talked about was that we have some value of x, and let's say this follows binomial distribution. Okay, so maybe it might be flipping a coin. Okay, so remember that you have n number of trials, and then you have P being the probability of success. So maybe, I don't know, it's 50-50, I don't know. Okay, so X follows some sort of distribution. Oh, and X is the number of successes. Okay, so we know that X follows some sort of binomial distribution. So the way that we call the sample proportion, or we kind of define it, is the following way. So the way that we write sample proportion is P hat. Okay, so if you want to write P hat, that's kind of how you say it. And the way that you kind of figure it out is just X divided by N. So the number of successes divided by the number of trials. Okay, so that's basically what P hat is. Okay, so if you want to think about it, if we do some example, so let's say we flip 10 coins. Okay, so flip 10 coins, 7 are heads. Then in that case, my sample proportion P hat is just going to be X over N. X in this case is a number of successes, which is 7 out of the 10 coins. Okay, so, or 10 trials that we did. So 7 divided by 10 is just 0.7. So this is basically my proportion, my sample proportion. It's not the true proportion, okay, but it is a sample proportion, okay. So now if we think about sample and population, okay, so let's just do a little bit of a recap when we do sample and population. So let's say we have population, and we also have sample. Well, when we talked about population, we were talking about parameters, okay? And the parameters for a population were mu, sigma, and now P. So mu was just a population mean, sigma was the population standard deviation, and P is the population proportion, okay? So if I were to have a population here, so maybe this is my population. If I wanted to figure out the mean of this, the mean mu, okay, so we just will take every single individual and get and add them all together and divide it by the total. So like if we were finding GPA, that's what we would do. Now it's not possible for me to get everyone in the population, so we take a sample. And a good estimator for mu is X bar. And all of these guys, we don't call them parameters, we call them statistics. And the statistic for mu is X bar. The statistic for sigma is S sub X. And now the statistics for the true proportion is going to be P hat. Okay, so these are kind of things that we've learned in the very beginning of class. Okay, so kind of just reminding yourself of all of this. So this is so now going back to the proportion. So we were saying that P hat, we just solve it by figuring out what X over N is. Okay, and then we are able to find P hat. Okay. Now, something else that we know about the binomial probability is the following thing. We know that for binomial, our mean, mu is NP, and our standard deviation is square root of NP 1 minus P. So this is what we know, what we did in the previous section. So this will be for the binomial, and we'll talk about this in a little bit. Now, my question here is, okay, is going back to this thing. So I flip 10 coins, and 7 of them are heads. P hat was equal to 0.7. So if I were to flip these 10 coins again, am I going to get 7 heads again? Well, maybe, but I might get 6 heads. I might get 7 heads. I might get no heads. So I'm gonna get a whole bunch of different types of variability in the number of heads. So what we want to figure out is, okay, well, if I were to plot these in a histogram, or maybe in a dot plot, what is this going to kind of look like? Okay, so we're kind of taking this binomial x, converting it kind of to a proportion, and we're going to plot them. So what is that going to look like? So let's take a look at it. So I'm going to kind of simulate this in a little, in this way. So the way, let me show you basically what I'm doing. So the probability of heads, I'm going to be flipping a couple coins. I'm going to flip 5 coins, and I know that the probability of heads is 0.5. And we're going to be tallying all the proportions, okay? So let me show you. So let me compute. So now what we're going to do is you can just pay attention for this. You don't need to go into StackCrunch. What I'm going to do one run. So I'm going to do one simulation, okay? So I'll show you basically what I just did and what exactly does that represent. So basically what I just did, let me click on the run again. I flipped 5 coins. And what I'm doing is I'm counting the number of heads. Notice here I only have 1 head. So I'm going to take 1 divided by 5. That gives me 0.2. So what I'm going to do is I'm going to put a box or a little tally at 0.2. Okay, I'm going to do it again. Notice here I didn't get any heads. So I'm going to go ahead and go down to 0. Okay, I'm going to do it again. Now I only got 1 head. Okay, so I'm going to go ahead and tally up right there. Okay, and I'm going to do this many different times. So obviously this is going to be really annoying if we just do this over and over and over again. So I'm just going to go ahead and do 5 runs. You can kind of see that it's going to do it 1, 2, 3, 4, and then 5. So what it's doing is that it got all of the so here's like kind of like this number 4, kind of 3. So I'm gonna go ahead and put 3 out of 5, which is 0.6. Put a 0.6 there. Then I'm gonna do it again, right? And I got 2, so it's gonna be 0.4. I'm gonna do this many different times. So let's just make this a little faster. Okay, so let's just do this 1,000 times. So you can kind of see a little bit of normality here. You kind of see that towards the center, you tend to have 0.4 and 0.6 a little bit more often. And I can do this many different times, as many times as I want to. Okay, so what you kind of see is kind of like this normal curve. Okay, not quite exactly normal, maybe a little bit, but you can kind of see this normal curve. Now, what I'm going to do is I'm going to increase n. So I'm going to go back. And now let's say instead of flipping 5 coins, I'm going to flip 10 coins. Okay, so I'm going to do this again. I'm going to do 10 coins. Okay, so compute, maximize. Let's do this again. We're just gonna do 1,000 runs. You can kind of see that the proportions become more and more normal, okay, as n increases. So if I were to increase n by 100, so if I add a 100 in there, what is that gonna look like? Okay, do this many different times. You kind of start seeing this normal distribution, okay, and then you can kind of see, if you want to look at one of the samples, you can kind of see that for run number 970, you got 51 heads and 49 tails, okay? So now you start seeing that where exactly is the mean? Well, the mean kind of tends to be around 50-50, okay? So I'm doing this many different times. Now you might be wondering, okay, well, obviously it's going to be normal because it's 50-50. Well, I can change it. I can change this probability to be something else. So let's say maybe I wanted to do it 0.2. So let's say it's a biased coin. It tends to go on heads less times. And in this case, I only have, let's say I'm only running 10 times. Okay, so I have 10 coins, and I have the probability of heads being 0.2. Okay, so I'm going to compute. Do it again. Now you start seeing that this is not quite normal. It looks a little bit skewed, okay, because of this 0.2. So you don't get this normality all the time, okay? But now let's say with this 0.2, this still probability, let's go ahead and change the value of n. Let's change n to 100. Let's say I increase my value of n to now 100. Well, if I do that and I run it one more time, so you will see a normality. So there comes a point in the number of coins that I flip that it starts becoming a little normal. So we kind of are looking at the sweet spot. Okay, so basically what we're going to try to do is we know that the p-hats, all of our individual p-hats are going to look normal. Okay, so we can start seeing that my p hats, okay? So, so here are basically our observations. So what do we see? So our observations are the following. One, p hat gets normal as n increases. So if I increase the number of coins, it starts becoming more and more normal. Okay. Two, okay. What would be really good to know about the normal is that the normal has a mean and a standard deviation. Well, the mean, what would be the mean of p hat? So the way that we're gonna write it, so we don't get confused with this mean, we're gonna write me and then mu and with the little p hat on the bottom. So the mean of p hat, well, what exactly would that be? Well, I know that p hat is x over n. Okay, we know what this was. X in this case was a binomial distribution. The mean for a binomial distribution was NP. So it will be NP divided by N. Okay? Notice that the ends are going to go away, so I'm left with P. And this kind of makes sense because if you look at the simulations, see here how it was 0.2. Well, the expected amount of heads that I can get is about 20%. And you can see here at 0.2, you have the highest bar, okay, which is basically our P. Okay, so that kind of makes sense. Okay, now what is our standard deviation? Well, our sigma, and let's write p hat here. Well, remember the standard deviation for a binomial distribution was the square root of np, 1 minus p, and then divided by n. With a little bit of algebra, you will figure out that this is equal to the square root of p, 1 minus p over n. Okay, so this is what we kind of figure out. So p hat gets normal as n increases. Two, the mean of the p hat is going to be p, and the standard deviation is going to be the square root of p, 1 minus p over n. And then finally, the last thing that we kind of can think about is that there's a sweet spot at where it becomes normal, okay? So there's a sweet spot, or there is a point where it becomes normal. Now, when is it going to become normal? Okay, well, here is the first important, really important theorem, okay? So this is what we call the central limit theorem for proportions, okay? So go ahead and take if you want to pause the video, this is going to be really, really important. So it says that suppose p hat is a sample proportion from a binomial experiment, okay? So with n trials and probability of success p. So then the mean of the sample proportion is just p. The standard deviation of the sample proportion is just this guy, which is basically what we just said. So if n is drawn from a sufficiently large population and n is large enough, quote unquote, large enough, then p hat follows a normal distribution with a mean of p and a standard deviation of square root of n, a square root of p, 1 minus p divided by n. Okay, so this is basically just the normal distribution formula, okay? Like filling in the blank, what we did in the previous videos. Okay, now what we want to be able to do now is what does large enough really mean? Well, large enough just means this. This is really important. This is what you need to be able to check all the time. We need to make sure that NP is greater than or equal to 10 and N1 minus P is also greater than or equal to 10. Okay, which basically means that the number of successes is greater than 10 and the number of failures is also greater than 10. Okay, as long as this is greater than 10, we are going to get something that's binomially that's normally distributed. If it's not satisfied, then this is not true, and we get kind of what we saw in a little bit where it was kind of skewed. Okay, so this is a really important theorem. Okay, so we're going to do a couple of examples using this theorem and the sampling distribution.